Good afternoon, everyone. And my name is Zhang, student from the University of Electronic Science and Technology of China. And I'm very honored to attend this conference and present my oral report. The title of my report is Node Selection for Asynchronous Multi-Task Tracking in Heterogeneous Sensor Networks. My presentation is divided into 5 parts. First, I will briefly introduce the background of my study. As you can see, with the development of sensor technology, wireless communication, signal processing, and other technologies, it has become an inevitable trend for heterogeneous sensor networks to cooperate in detection to improve the perspection ability of the complex environment. Example includes the application in distributed airborne HSN and unmanned HSN. To further enhancing the system capabilities, resource scheduling algorithms plays a crucial role in optimizing the performance of the heterogeneous sensor networks by reasonably allocating limited resources such as radar beams and its power and some sensor nodes. The following diagram demonstrates the operation of the sensor network after resource scheduling. Where the system manages each sensor node based on the state of the target, thereby improving the system performance. Here we summarize some key points of the heterogeneous sensor resource scheduling. Firstly, it can bring benefits such as the increased detection capabilities and the expanded detection field. And it will bring higher tracking accuracy. However, it also faces some challenges, such as increased system complexity and scheduling difficulties caused by the asynchronous signal processing with a higher degree of freedom. In our research, the goal is to design a schedule method for asynchronous multi-target tracking in heterogeneous sensor networks to improve the overall performance. Next, I will provide a detailed description of the heterogeneous sensor system in our study. Firstly, we consider a heterogeneous sensor network consisting of N phase array radar and M infrared sensors. Working cooperatively to track the point-like Q targets within the civilization area. In such a network, radars and IR sensors have different revisit times, so a common time interval must be set for their operation. Therefore, we define the resource schedule interval as T. Within one RSI, each radar can revisit targets DR times, while each IR sensors can revisit targets DI times. Specifically, we provide a workflow diagram for the case RSI, where 3 radars and 2 IR sensors track 2 targets with DR equal to 3 and DI equal to 2, respectively. Subsequently, we define the selection matrices for radars and IR sensors, which are the key optimization variables. These matrices determine the correspondence between the sensors and targets, where SRNQK equal to 1 or SIMQK equal to 1 indicates that target Q is being tracked by the radar N or IR sensor M. Then, the target motion model is shown in the diagram on the left. All targets move independently within the civilizing area following a constant velocity model. Mathematically, we assume the state vector of the Q target at time t as the 4-dimensional vector. The first and the third dimensions represent the target's position in Cartesian coordinates, and the second and the fourth dimensions represent its velocity. The transition of the target can then be expressed in the following form. The state of the transition of the target can be expressed in this form, where F denotes the transition matrix and V represents the noise typically assigned to be a zero mean Gaussian random variable. Based on the target motion model, we can separately model the measurements for the radars and the IR sensors. The radar measurement is modeled as a two-dimensional vector containing radial distance and azimuth, which can be seen as the true radial distance and azimuth overlays with a Gaussian white noise. In contrast, since IR sensors usually only measure the azimuth, we model its measurement as a one-dimensional variable. So it is important to know that the quality of these measurements often depend on the signal-to-noise ratio, which is controlled by the system and the environmental parameters. So the SNR serves as the basis of our node selection. Then, as we mentioned, SNR affects the measurement quality and therefore the question accuracy. So by selecting different nodes, select different nodes to track different targets, we can obtain the higher quality measurements and improve the tracking accuracy. So mathematically, the node selection problem can be modeled as an optimization problem. So as shown in the diagram. After solving it, we can obtain a node selection strategy to guide the further target tracking. The key is to describe the node selection problem as a mathematical optimization problem and solve it. So, as we know, the two key points of formulating an optimization problem are design a utility function and determine its constraints. So here we define the worst tracking performance as the utility function to describe the system performance. It is the maximum of the all Q target tracking performance defined as the strength of the predicted Cramér lower bound. Theoretically, this one provides the lower bound of target tracking. Next, the system constraints are described. The left one as the blue one. The left one describes the correspondence between the targets and sensors, and the right one ensures the each sensor tracks only one target. Based on the utility and function, and the system constraints, the node selection for AMTT in the HSN can be formulated. And as mentioned earlier, the utility function represents the worst tracking performance. So by minimizing it, we can make the tracking accuracy of all targets generally converge. Specifically, we have provided a simulation diagram showing that the HSN PCLB of all targets generally converges after the simulation starts. Finally, after solving the problem, the node selection strategy can be obtained, which guides the target tracking process. Here we present the target start estimation process during the tracking. As you can see, the radar and the IR sensors derive their local posterior starts independently, and these local posterior stats are sent to the fusion center to enhancing the tracking accuracy by the information fusion. This method ensures that the posterior information obtained from the heterogeneous sensor nodes is in a unified format. Then we conduct the simulation. Experiments to demonstrate the effectiveness of the proposed algorithm. In the simulation, we consult an HSN consisting of 3 radars and 2 IR sensors. with 3 targets moving within the stabilizing area. The reader revisit time was set to 2, and the IR revisit time is set to 4. The IRS is set to 1 second, and we analyze 40 tracking farms. So some parameters of the simulation are shown as follows. Then in the simulation, we firstly verified the performance gain brought by the heterogeneous sensors compared to the homogeneous sensors. We provided the tracking accuracy of the proposed algorithm is only IR sensors, only radars, or only all sensors are activated. Next, to verify the effectiveness of our algorithm, we provide the target tracking accuracy results obtained by the random allocation algorithm. So this algorithm, the sensors are randomly assigned to tracking targets without node selection. So to reduce the randomness of the experiments, we then conduct 1,000 Monte Carlo experiments and calculate the root mean square error, which are given along with the PCLB. The results are shown in the following diagram. Finally, since the system performance is measured by the worst PCLB, we compare the worst PCLB of 4 algorithms. So as you can see, the joint detection of the heterogeneous sensors achieve better performance compared with the homogeneous sensors. As you can see, the purple line is always under the blue one and the orange one. So after that, the proposed algorithm also performs better than the random allocation algorithm. So it's demonstrating the effectiveness of our algorithm. So as you can see, the purple one is always under the blue one, the yellow one. So in conclusion, we summarize our work and outline the future directions. Firstly, we proposed a node selection framework comprising multi-faceted radars and IR sensors for IMTT in HSN. So secondly, we formulated and solved the node selection problem. Thirdly, the simulation result demonstrates the effectiveness of the algorithm. In the future, we will explore more degrees of the freedom, such as scheduling the transmission power and consider other heterogeneous sensors like optical sensors. At the same time, the current research is limited to simulation experiments. So the future engineering realization will be one of our future goals. That's all of my speech, and thanks for your listening, and welcome any questions.